Okay, in this section we'll talk a little bit about working with materials which are not metals, like plastics, ceramics, and so on. So the most useful engineering plastic in normal R&D work is polycarbonate, which is mainly known as under the trade name Lexan, GE trade name Lexan. So polycarbonates are amazing materials because they are shatterproof and ductile. So you can take, this is 3/16 polycarbonate, you can bend it as if it was sheet metal and it doesn't break. And that's a beautiful property. It does spring back a little bit. That was supposed to be a 90-degree break, so it springs back a little bit, but it's not a problem because you can bend it sharper than 90, it will spring back to 90. The only disadvantage of this, in terms of building stuff out of it, that it wouldn't hold threads because it's too weak to hold a thread. And what you have to do is to use either inserts. These are threaded inserts that are set like pop rivets, or use helicoils. If you don't have room for the inserts, you can use helicoils. Helicoils are little metal springs which form a thread. You thread them in and they stay in place. So you can see here, this is a plain hole, and these three have helicoils, and then the helicoil provides an excellent thread. So once you do that, the rest of the part is very usable like metal. But a few precautions. First of all, these materials are all unstable. They absorb, all plastics are unstable materials unless they're heavily filled with some filler like fibers or so on, because all these materials absorb humidity, they change with humidity, they soften with temperature, and they also have a much larger thermal expansion coefficient than metals. So typically, as we said, metals like have an expansion coefficient between 10 and 23. Say steel is about 11, aluminum is about 23, brass is somewhere in between steel and aluminum. Plastics have a temperature coefficient typically between 50 and 150. So almost an order of magnitude more than metals, and it could be problematic. So if you bolt down a plastic sheet to a metal sheet at the corners, you put it in the sun, it will buckle. The plastic will expand and buckle, because 100 ppm is a big problem. 100 ppm over a meter is 0.1 millimeter per degree. 10 degrees is 1 millimeter, so it's a huge expansion. So it's a big concern. The expansion is a big problem. Stability is a big problem. So you can't really, if you can avoid using them, it's better. But sometimes you need heat insulation, electrical insulation, transparency. Then you use them. But think of it, if this was a big sheet, it's better to mount one side with a fixed screw and the other side with a slot and some washer so it can expand. Okay, so let's talk for a couple of minutes about ceramic materials, because a lot of times you need to use a ceramic material either because you need a very high temperature resistant material, or because you need a material which is a very good electrical insulator and high temperature. Otherwise you could use plastic. For example, you have to make heaters, crucibles, so you have to use ceramics. So there's a few choices here. Like a very good choice is materials called machinable ceramics. These are ceramics which can take a very high temperature, but they're actually quite machinable, as comparable to aluminum. For example, this is a material known as mica-lex, which is a glass mica composite, and it will take up to about 1,000 degrees. You can file it. You can file it just like metal. So if I can file a notch in it. I don't know if you can see it here, but it just has about the machinability of aluminum in terms of how fast you can drill it or file it. It's a very nice material. It keeps a very good finish. It's a very stable material. The only problem is that it's becoming more and more rare and therefore expensive because nobody knows about it, so nobody orders it, so it's being phased out the market, which is very sad because it was one of the best machinable ceramics. It's being replaced by much more expensive machinable ceramics, which are no better, like Micor and so on, which are similar to that, but are brand names. And this used to be a dirt cheap, popular material. Okay, you can even make it yourself. It's a simple material to make. But you can get machinable alumina today quite readily, And the same machinable alumina can be fired to become very hard, but you can still use it without firing. In the machinable state, looks a bit like this. Another very interesting machinable material is boron nitride in the hexagonal form. Okay, so this is, some people refer to it as white graphite. This is very much like graphite, has fantastic lubricity properties. It's self-lubricating, it feels as if it was oiled. So it's very good to make bearing, sliding surface, but it can take a very, very high temperature. I don't remember offhand, but it'll take at least 1500 degrees, maybe even higher. And it has a low temperature expansion, very, very easily machinable, and not that expensive. It's a great material overall. It's just not that strong. It's not hard, of course, because machinable, and it's not strong, but if you don't need the strength, it's one of the best materials. So for example, I'll file a notch in it. So you can see it took about as fast or even faster than this. And it's completely inert, completely slippery, has a beautiful finish. As I said, it feels like it's always oiled. So boron nitrate, white boron nitrate. You can of course buy hardened alumina parts like pipes and plates and rods. This one you cannot file at all, it will just ruin the file. The black mark you see is the alumina actually filed the file, not the other way, that's why it went black. Okay, it's much harder than the file. Very hard, very brittle, very strong. Alumina is one of the strongest ceramics. So if you can find something which is the size you need, like a pipe or a rod, you can just buy that. That's very simple, inexpensive. You can cut it with diamond tooling. You can grind it, cut it, but it has to be diamond tooling. Okay. Poor man's ceramic that is quite versatile and very cheap is slate. Slate is what people used to make roofs of, and still people make some counters for them and so on. So in every town, in every stone shop, you can buy slate. And these come as polished panels, anywhere from 1 foot by 1 foot to big panels. They are dirt cheap, like a 1 foot by 1 foot polished slate panel is under $10. It's machinable very much like the boron nitride or like the mica lex. For example, if I try to cut here a slot, you can see the slot here. It's about the same speed. If you watched how long it took to cut a slot, all these materials are very, very comparable. They're all comparable to aluminum in how fast they machine. Now, the slate can be sanded beautifully. This edge is sanded. This is hexo cut. Can be water jet cut perfectly. All of these, by the way, cut with water jet. All this is water jet cut. So all of them water jet cut perfectly. Okay? So basically all can be tapped, threaded, tapped, everything. The same as this. You don't need thread inserts. All these materials can be tapped, except the hard alumina. So the only disadvantage of slate is that if you heat it up near 1000 degrees, it will delaminate. Because slate is a layered material. That's why originally it was used. It separates easily into layers. So if you design your part in such a way that there are no strengths needed in this dimension, then it's not a problem. For example, if I have some heater panel and I have to clamp it down with screws anyway, I don't care if it'll delaminate inside because there's no force this way. So as long as you design the parts in the right direction, slate right now is the cheapest and best ceramic to use for everything. Okay, but because it's not omnidirectional, it's not as nice as, say, mica lex, because this has the same properties in all directions. Okay, now, and the last ceramic material I want to mention is zirconia. Now, zirconia is a more exotic material. It is a ceramic with one of the highest hardnesses, the highest strength, and the highest melting point. So it is the best of all ceramics, especially if you need thermal insulation, because alumina is strong, hard, but it's not a thermal insulator. Zirconia is stronger than alumina, harder, and a perfect thermal insulator. So this is a magic material, zirconia. It's expensive. It's about 5-10 times more expensive. But it has an interesting advantage, because for R&D work, people use it today to make crowns. or other parts for teeth. So which means that you can buy these blocks of zirconia anywhere, and these are soft. They are called green-fired. So it's a bit like the soft alumina you can fire into hard. So the soft zirconia, which is semi-fired, can be machined, and again, if we look at the cutting speed, again, very, very similar to the other ceramics, how long it takes to make a cut. Okay, again, like aluminum. So this is the same. So if you need some very exotic part, especially if it's small and it has to take 2000 degrees, enormous pressures, totally inert, every miracle property combined, you can buy yourself one of those, which is a blank for dental inserts, machine it on a regular milling machine or a file, and send it to any dental lab to be sintered. Not sintered, but fired. Because this is half fired, okay? Now once you fire it, it becomes a material which cannot be machined at all except with diamond tooling. So here, when I do that, I get the same problem as the alumina. It turns black because it's eating up the file, okay? So this is actually very similar to carbide, to tungsten carbide in properties. If you take a chip of this, put it in the lathe, it'll cut steel with no problem. There's actually cutting tools made of ceramics, but even the regular zirconia mounted, I tried it, and it will cut steel very nicely. So this is a ultimate material, but expensive. Like a thing like this, I think cost about $100, compared to a piece of slate this big, which costs $5. So this is an expensive material, but it's irreplaceable if you want a very intricate part that you have to make yourself. One thing to keep in mind, when you fire that, the linear dimension shrinks a lot. And it shrinks in the order of 20%, sometimes even more, 30. So first of all, they give you the shrinkage factor. Like before you make the part, you have to find out the shrinkage factor. The shrinkage factor, actually I can tell you, because all that you need to know is the final density, and the density here, it takes the cube root, okay? So the final density of this is 6. The density here is 3.6, yeah, so it's about 17% or something like this, 15-17% shrinkage factor. So it's not as bad, but you have to, it's quite predictable, it's omnidirectional, but you have to scale all the dimensions with the shrinkage factor. So these parts, these are special pistons. They were made from a blank like this, from zirconia, and after firing, they were finished diamond machined. Because of the slight uncertainty in the shrinkage, you want to leave, say, 0.1, 0.2 millimeter, and then you diamond machine it with a diamond grinding wheel. But these are amazing parts in terms of performance. One material which has an unusual property is glass, and the unusual property is that if you make a shape in glass, like a prismatic shape, for example, we ground this to a D-shape cross-section, if you heat up the glass and draw it, it will become thinner and thinner, but it will maintain the shape. Even if you ground it to a very sharp corner like this has, and you draw it to be 100th of the diameter, and you look under a microscope at the piece, the sharp corner will be retained. The accuracy of retaining the form is about 1 micron. And of course, it's a predictable process, so even if there is an error in retaining the form, the error is repeatable. You can measure it and grind the preform with the error included. So you can actually get sub-micron accuracy after one pass where you measure the error. So this has to be done in a proper oven, which I don't have here, but just to show the principle, I'll just do it with a regular torch, and you have to heat it kind of gently in order not to crack it. Starting to soften. It's not to be a bit hotter. Maybe I'll do it like this in the flame. Okay, now again we have to let it cool down nicely, not to crack it. Also has to be done at the right temperature, because if you make it too soft it'll all flow together. So you have to be careful. I'm not sure if it's the right temperature. Yeah, but it worked. Yeah, it maintained its shape perfectly. Okay. So now what we'll do is we can see that it maintained its D-shaped perfectly. Okay, so the same demo you just saw a minute ago about drawing glass, keeping its cross-section shape, is a very unique property which I realize most of you will never need, but if you ever need, there is no substitute to this quality. And the main use of this property is to make cylindrical lenses, miniature cylindrical lenses. For example, this is a slice from a 1-foot bar ground on a CNC grinder to an aspheric profile. This 1-foot bar was heated up in the oven and drawn into these lenses. So out of the 1-foot bar, there was a few hundred feet of these lenses which came out, and these are nearly diffraction limited, aspherically corrected cylindrical lenses, which are used to manufacture the special micro lenses for lasers. So basically, later on they are cut up and installed in a mount like this. So it's a very esoteric use, but if you need this kind of prismatic shapes, squares, triangles, aspheric lenses, it's the best process to manufacture them.